I'm Robert Bridson, Senior Principal Research Scientist with the Bifrost Group. I'll be giving an overview of the Aero solver, the math and the algorithms behind it, as well as talking about our new improved time integration, both what it is under the hood and what kind of improvement you get out of it.
The first thing I should emphasize is that Bifrost Aero is an Eulerian solver. What does that mean? Well, basically, it boils down to how we sample the world. And instead of sort of tracing particles through the flow or tracking the smoke with other structures that move with the fluid, we instead sample things on a fixed spatial grid of some sort. So we sample quantities like the fluid velocity or temperature or smoke density, fog, at fixed corners of grid cells in space. And we try and figure out how the values that we'd sample there evolve forward in time, even though the fluid might be flowing past them, through them. We don't have any particles in this solver. This is different from our liquid solver, which uses the flip method, which combines both particles to sample the fluid with a background grid or something a little more complicated I'll talk about in 1 second to solve for the physics underlying the motion. When I say we use a grid, that's not strictly true. What we have is, for all our volumetric data structures in Bifrost, is something we call the tile tree, which is a little more complicated. It's an adaptive or multi-resolution data structure. And, well, the name really says it all. We divide space up. Our basic unit is not a single grid cell, but rather a tile of grid cells. So a three-dimensional tile of a configurable dimension, but for Aero, normally we use 4 by 4 by 4 by 4. So let me just draw an awful image here of a tile. And this tile represents a contiguous chunk of memory where we have all these data values close together, so it's great for cache performance and so on, and reduces the overhead of the data structure for where we place these tiles in space. But it's a small enough tile that, apart from the data locality, we can also be very efficient about instantiating these tiles only where we need the data. And where it gets adaptive, where we have the multiple resolutions, is that we actually have tiles of different sizes in different parts of space. So we may have tiles, for example, with grid cells of half the size, or a quarter of the size, or an eighth of the size, and so on. We can have a whole hierarchy of different resolutions. And we arrange all of this, we store all of this in a tree. You're probably familiar with octrees or quad trees. This is the same idea, it's just we've generalized it. So where I'll just draw a quad tree in 2 dimensions, but it's the same thing as an octree in 3 dimensions. You start with a square that covers all of space, and then you can refine it. And every time you refine it, you split it up into 2 by 2. And each of those subcells you could split up as you want, not necessarily all of them. And you can keep refining to whatever maximum depth you go to. So we do the same thing, except instead of always splitting by 2, we can split by a defined user parameter. So in the liquid solver, we tend to split by 5. In the Aero solver, we often just split by 2. And then instead of just having a single grid cell here, we actually use tiles. So we can have a very efficient, as performant data structure to capture all of this. And finally, let me talk a bit about the volumetric channels that are in play in our solver. So there can actually be many channels, and it's possible to add others. The most important, though, is velocity, which in the math behind the fluid dynamics, we usually use just the letter U, sometimes with a vector, sometimes we call the 3 components, horizontal, vertical, and in and out of the screen, UVW. I'll just say U. And this is a 3-dimensional vector, so we might say it is a float 3 type. And this is actually worth mentioning. Unlike some fluid solvers, we actually store this as 3-dimensional vectors sampled at grid cell corners, which would seem to be the obvious thing, right? There are a lot of fluid solvers out there which use a different arrangement, a staggered grid arrangement, or sometimes it's called a MAC grid, where they split up the different components and store them in different locations. So maybe the horizontal velocity would be at the midpoints of the faces which are perpendicular to the horizontal axis, and the vertical velocity would be stored at the midpoints of the faces that are perpendicular to the vertical axis, and so on. And you can do that in 3D too. It's kind of a weird way of thinking about things. It happens to make the pressure solve on a regular uniform grid really easy and well behaved. But on the other hand, it means things like interpolating a 3D velocity vector at some point in between, kind of expensive because you have to interpolate the horizontal component with different weights than you would interpolate the vertical component, and so on and so on. And it's just a real inconvenience and an expense doing any kind of processing of vector fields with this. So we don't do that. Anyhow, since we're using a tile tree, it turns out the whole thing of making it easier for the pressure solve doesn't really help us. We also have fog, or fog density, which would be kind of a basic idea of where the smoke is and how thick it is and so on. So generally this should be non-negative values. And then, of course, we may have other fields too, other channels like temperature, and there's a whole bunch of things that may be important for combustion, which we'll talk about in another section of this video. So that's what's kind of the basics of it. Now let's talk a bit about what we're actually solving. What does the simulation really do? So the most important equations are the incompressible Navier-Stokes equations, which have been around for centuries and have been shown to be extraordinarily accurate, excellent physical models for things like air and water in sort of everyday scenarios. So not talking about, rarefied gases way up high in the atmosphere, not talking about super compressed, supersonic shock waves or anything like that, but, just talking about the kinds of things that humans have an everyday experience with. It turns out this is an extraordinarily good model. It's very difficult to solve these partial differential equations. We can only get approximate solutions, and things like turbulence are a continual mystery to the world's scientists, engineers, mathematicians, but we still have very good methods. What are these equations? Well, it's two coupled partial differential equations. One, which is sometimes called the momentum equation. It's really actually just Newton's second law, F equals ma, in disguise. But it's written in what looks like a kind of crazy way, normally. But I'll go through this and explain it. And then the other equation is sometimes called the conservation of mass. And for us, it ends up being actually a constraint on the velocity field, which I'll explain in a moment. Actually, let's start with the conservational mass first. So this is the divergence operator on our velocity vector field. You could write it out as the partial of the horizontal component of velocity with respect to x, plus the partial derivative of the y component with respect to y, plus the partial derivative of the z component with respect to z, all equal to 0. So when you add these up, you should be getting 0. What does that mean? Well, I'll just draw this looking at, say, a little volume of space, a grid cell. Really what's going on here is this derivative, this difference along the x-axis is basically saying if this was like a super tiny infinitesimal cube of fluid, or cube in space through which the fluid is flowing, if I measure the velocity on one face and subtract off the velocity on the opposite face in the x direction, that's really what this derivative is measuring. So how the velocity is changing, and the horizontal component of velocity is changing in the horizontal direction. And this one is also like the difference in the vertical velocity in the vertical direction, and so on. And in a sense, what this is saying is I'm taking the rate at which things are flowing out of this face minus the rate at which things are flowing into the opposite face. And the same thing for all the other opposing faces. So really this is measuring how fast is fluid entering or exiting a region of space, a tiny region of space. And what we're saying is that by setting this to 0, I'm saying there should be exactly as much fluid coming in as there is going out. So the net flux is 0. And this is basically saying that the fluid conserves its volume. And although I'm sure I've heard if that's always true for liquids, you might be saying, well, that's not quite true for gases because you can like compress them in a pump or things like that. But of course, those are unusual situations, and most of the motion is governed, it turns out, very accurately by this constraint. So let's go back to the other equation here. This one has a lot of complicated terms. Let me look at this right-hand side first. This is what's called the viscosity, viscous contribution. Eta is the kinematic viscosity, and it measures how like sticky the fluid is, how much it resists deforming or shearing past itself. So, something like honey or thick oil is very viscous, has very high kinematic viscosity. Air has a very, very, very low kinematic viscosity, and water has an even smaller kinematic viscosity. In fact, it's so small that we're basically say the tiny effect this would have is visually unnoticeable, and any like serious effects it may have on the flow are more than covered for by actually the numerical errors we make in other parts of the algorithm. So we're actually going to say that this is 0, and we ignore this term. Down the road, it turns out that's true almost everywhere except in the boundary layers that develop as flow goes past a solid. Turns out viscosity actually is important there, because even though the kinematic viscosity coefficient is tiny, this other term, the Laplacian of velocity, can be really big. That's a pretty intricate effect. We're going to be tackling it down the road, but for the moment, we kind of just let the solver do its own thing around there, and it looks good enough. This term, what's going on here? Well, rho is the fluid density, and don't get confused here with something like the concentration or density of fog or smoke or soot or whatever in the air. This is really like the density of air. So this is like typically 1.3 kilograms per meter cubed for air at regular temperatures and pressures. Obviously for other fluids it would be different, but it's not something necessarily that you're looking at. It's just, we basically think of this as being essentially constant throughout the volume of the fluid. And P is the pressure, which I didn't mention on the previous drawing about channels that we track. It does turn out to be a channel that we use internally, but it's really just used internally to satisfy the constraint here, that the fluid maintains its volume. So pressure forces act to prevent the fluid like concentrating inside one cell or leaving another cell. We figure out the pressure that will even things out. And then the last part of this equation is really these two terms combined. And this is sometimes called the material derivative. And it's really measuring the acceleration of like particles of air, molecules of air. And sometimes people write it with a big D like this, which is the same thing as saying the partial derivative with respect to time. So that's kind of how fast is the velocity changing at one of our grid cells. But that can be due to two things. It could be due to like pressure forces and stuff changing the velocity, accelerating the fluid. But it can also be due to what we call transport, which is just one bit of fluid moves away and a new bit of fluid comes into the grid cell, to the sample, that has a different velocity. And we account for this with this complicated nonlinear term, u dotted with the gradient of the velocity. This is where all the nonlinear magic of fluids comes from, this nonlinear term. I mentioned this word transport. Let's look at that next. This is a critical part of our solver. So like many fluid solvers in graphics, we break up the momentum equation into different stages, and transport is one of the most important. So this sort of takes the state of the fluid and basically flows it through the grid or the tile tree to the new time step. By the way, I should mention here, although I sort of am hinting at the tile tree being like this fixed in space thing, it's an entirely dynamic data structure. So under the hood, every time step, the tile tree can have a different refinement pattern. And basically, we allow the solver to figure out, based on the physics, on sort of the detail in the flow, and based on user constraints, something like saying, I want things close to the camera or, in shot to be more refined than things that are far away and I won't really see. We let the combination of the solver and user input decide where things should be refined, and that can be dynamic. It can change every time step, and you'll see examples of this elsewhere in this video. Anyhow, transport takes the state of the fluid, so things like velocity and fog and so on, and just flows those quantities through the tile tree to the new time step with the velocity field, with the fluid's velocity. But it doesn't do anything else, and nothing else. So no pressure, no physics. So it's purely, you could view it as we have a particle system. Each particle has some values on it, and we just move those particles around without changing the values. That's what transport is. Except for us, it's more complicated because, like I said, we don't have particles. We just have this fixed grid. We use what's called a semi-Lagrangian scheme, which, if you know anything about fluid solvers and graphics, it should be familiar with you. Autodesk's own Yostam popularized it as the stable fluids method, as a particular example of a semi-Lagrangian scheme. And you can think of this as basically saying, if we have our time or frame n grid here with some values sampled on the grid there, and the fluid is sort of, I'm just going to say it's generally moving in this sort of diagonal direction. I mean, this could be swirly and everything, but I'm not going to try and draw all that detail. And now I have a time m+1, or frame m+1 grid. And basically, all I want to do is figure out if, for example, I had a particularly foggy patch here, how can I come up with the fog values in the new grid, knowing that this fog should have flowed along the path here? Well, what I can do is say at this grid cell, I know the fluid was coming in this direction to the new grid point. So the new value of the fog here should be the old value of the fog back here when I trace back through the velocity field. And so if you do this at every grid point, sort of trace back and then interpolate in the old grid, you get the transport of whatever channel it is. So we do that for things like fog and temperature, but we also do it for the velocity field itself, which is a little mind-bending because we're moving the velocity field in the velocity field. But one is fixed, sort of we fix how things are flowing, and then we trace any channel, and it doesn't matter how you interpret that channel. There are two parts to that. We have to trace back through the grid. So we use a fairly advanced ODE solver, a Runge-Kutta 3 method, to trace back. And then we need to interpolate the value in the old grid, or the old tile tree. Of course, the simplest thing would just be to use linear interpolation or trilinear interpolation, LIRP. And this is an option. It's fast, but it tends to smooth things out. So we sometimes call that diffusive. which for some simulation scenarios, that's actually a nice effect. Things get smoother with time as they trend apart, and you see, like fog or steam dissipating into a smooth generic field. But if you want like really detailed, pyroclastic looking smoke, this is maybe not the look you want. So we also have, for example, a sharp cubic interpolant, which is expensive because it has to look up a lot more data and do a bit more math, but it gives super sharp results. And sort of well-defined fluid patterns or smoke patterns sort of persist really well as they move through the grid with this one. Okay, so this is kind of half of the simulation, is transporting things around. The other half is figuring out the dynamics, or how things should be accelerated. And the most important thing really is incompressibility, at least for plain vanilla smoke. When we talk about combustion, there's a whole other world of things going on, chemical reactions and flame fronts and so on. But for regular smoke, we have incompressibility, or really it's the pressure solve. So what pressure is required to satisfy that the new velocity, after we incorporate the pressure forces, should preserve volumes, or sometimes we'll say, because this is the divergence operator, we might say it's divergence free. And it turns out, so I'm just going to sketch this in 2D. If we have, say, for example, the fluid is trying to concentrate all in one grid cell, and so it's getting squeezed here and not really over here, then we might say we want high pressure here and low pressure here. So the high pressure will force the fluid to not squeeze into this grid cell, but instead sort of balance between the two. Of course, the thing is, it's all globally coupled. So if we put a high pressure here to fix this, then it might push into the neighboring grid cells over here, and we might have a divergence problem in there if now suddenly the fluid is pushing into there, and then if we fix that with a pressure there, it can cascade over. So really this is kind of a globally connected problem. It turns out, I'm not going to go through all the math here, but it ends up solving what's called a Poisson problem, which in differential equation form looks something like this. But basically, this means we have a big linear system for all the pressures. And we'll have a pressure for every grid cell in the tile tree that is an unknown that we have to solve for. That system can be expensive and slow to solve if we were to do it with traditional, or the old methods like Gaussian elimination that maybe you learned in high school. It turns out we don't actually care if this is absolutely exact. The other errors that are made in the solver may actually be larger, and as long as we balance the errors so one isn't like obviously causing a visual problem, it's fine. So what we use is something called multigrid, which actually works very beautifully with our multi-resolution tile tree. And the idea is that we will solve the problem by first doing something simple, like fixing each pressure according just to its nearest neighbors, and not trying to take into account larger influences. That will resolve the smallest details of the pressure problem, but it will leave behind sort of smoother errors in pressure and divergence. So let me try and sketch this then. We do a cheap solve on sort of very fine grids wherever it's refined. And then we transfer the error, which we think now should be smooth because we've fixed all the high resolution bits with a local thing, to a coarser grid. where we repeat the same thing. And now these big cells, when we do just nearest neighbors, are actually talking about larger skips in space. And we eventually work our way down to a giant grid cell that sort of covers everything. And then we interpolate back. And as we go, we keep fixing errors at the appropriate resolution. So it's kind of a multi-resolution strategy. And in every resolution, we're using an efficient solver for the resolution, for the scales of error at that place in the continuum of resolutions, grid cell sizes. Multigrid is a great fast solver, and it scales linearly with the problem size, unlike a lot of linear solvers. The one problem multigrid has is if we have a solid object in here, it gets a little bit hairy to include it in all the different resolutions. You know, if it's smaller than a grid cell at the more coarse sizes, then it's a little hard to figure out how to incorporate it into the linear systems there. So instead, we use something called iterated orthogonal projection. So we do a multi-grid pass to make the fluid respect volume conservation, and then we make sure that it also respects solid boundaries, so any colliders you have in the flow. You don't want the fluid to go through the collider. If I've got what looks like a sack of potatoes here, I want instead to fix those velocities to go around my sack of potatoes. And I can do that locally, just around the boundary of the solid, but that may screw up the volume conservation here. So then if I go back and fix the pressure, and then I go back and do this, if I iterate between that, it actually does converge to the right solution. And that's a parameter you can control depending on how much fidelity you want. But of course, the more iterations back and forth you go, the slower it is. So that's the basics of our fluid solver. So time integration is just the fancy term for moving the simulation forward in time. Because it's a differential equation we're solving, the opposite of derivatives is integrals. So integrating the differential equation in time, like solving it, is called time integration. I mentioned when we were talking about transport that particularly if you use linear interpolation or lerping, it can smooth out details much faster than you want, faster than the physics say they should be smoothed out. That's sometimes called numerical diffusion. So it looks like a physical diffusion, but it's due to numerical errors, and we don't like that. So partly when we're talking about fluid flow, it can be due to low accuracy transport, but the sharp cubic interpolant that we offer more or less fixes this. It improves the accuracy of the transport enough that you don't have to worry about it. But that's not the only cause for losing energy. The nature of first-order time integration also can lose energy and interest in the flow. So we had to come up with something to improve on this. Let me talk a bit about this. So the simplest solver, like the first-order solver, looks basically something like this. We start with the velocity at time n. We transport it and other fluids like fog or temperature or whatever to the new time. But since we only do transport and we don't do like the other physics, I'm going to say this is just going to be like u tilde n plus 1. And then we solve pressure to get the final one. So this is solving basically du dt equals 0. So it's moving the fluid through space, but it's not including any of the pressure forces. And this is basically, it's adding or subtracting the pressure gradient I should put a time step in there just to be correct. and it's making the divergence of the new velocity field 0. So we've kind of split apart the original differential equation, the momentum equation and the conservation of law, into two different stages, and we're doing them one after the other. And unfortunately, that's like not completely correct. There are all kinds of effects that interlink these terms, and we can't, to first order accuracy, we can say, while I'm transporting, I'm going to say that the pressure gradient isn't changing at all, so I can ignore it, or there's no pressure effects while the fluid is moving, and then it's only after it's moved that I incorporate the pressure. And to first order accuracy, that's good enough. But there are, in fact, all these errors I'm making, higher order errors, that have everything to do about the fact that, in fact, as the fluid moves, the pressure forces are changing and adjusting it to always keep the divergence 0. This is still pretty abstract, so let me sketch out an example of really how this goes wrong and how you would see it. So imagine a flow that's just going to be a rigid rotation. So it's basically going round in circles. And I'll look at, say, a few particles just as sort of representatives on one of these sort of circular orbits as the flow goes around. And what happens if I had perfect transport? So I'm going to assume no errors. So it's as if I actually was tracking every single molecule of air and looking at its velocity. What would happen? Well, this guy is moving of course, perpendicular to the circle. And those ones, I'm going to sketch out what their velocity looks like. So this is un, the original velocity field. Now what happens when I transport these particles, but I do nothing to change their velocity? I'm just moving the particles, but keeping all the values they're carrying the same. Well, if they move around the circle, so this guy at the bottom, I'll add an extra circle around him so you can see where he moved from. He'll move up around the circle, and let's say he gets, 2/3 of the way to the side. He'll move there, but his velocity is still identical to what it was down there. And same thing with this guy that was at the side. He'll move up, but his velocity is still pointing straight up. And this guy who was at the top will move down, but his velocity is going to be pointing straight out, and so on. And what you'll notice is if you filled in all of the velocities, I've just given you 4 representative points, but basically, instead of just spiraling around, in fact, we're no longer really going around very much, we're mostly going out. It's like it's exploding now, it's expanding, which violates the conservation of volume. So when we fix this with the pressure to make it divergence free, what's going to happen is that it's going to project out the bad component of velocity that's going outwards and just leave us with the part that's tangential. But it's going to be a lot smaller. What we're left with is only a fraction of the original velocity. So the whole thing, through the time integration, sort of one time step, basically slows down rotation. And rotation really is the most important part of like a smoke plume or an explosion or anything like that. It's all about how things swirl and rotate and so on. And if our time integration itself keeps sucking the energy out, the angular velocity out of those rotations, it doesn't look so great. We can get around this with lots of time steps or, just adding a lot of force and hoping the shot goes by fast. But ideally, we can do something a bit better, which we can. So I'll talk a bit about constrained or stiff dynamics. and this is going to get a little mathy, I'll apologize. But if we have a differential equation, and I'm not even going to use velocity or anything, I'm just going to say dy dt is f of y. If this f somehow represents like a really stiff force that almost basically is constraining y in some way, it turns out there's this whole theory of differential equations that say implicit integrators are the way to go. What an implicit integrator would do would be to, well, in particular, the best family is what's called the backward differentiation formulas, or BDF. There are actually many, many stiff integrators out there, but almost all of the other ones that are fully accurate for these kinds of constrained problems are a lot more expensive than the BDF formulas. And so these are the ones we tend to stick with for reasons of performance. But basically what we're going to say is I'm going to approximate this equation at time n plus 1, both sides. So I can do a finite difference on the left-hand side. So the simplest one would be to say that the difference between the new value of y and the old value of y divided by the time step. And I'm going to say is going to equal a forcing function, which makes our constraint happen or whatever, evaluated at the new value of y. And because I have y, the new unknown value of y on both sides, this is a system of equations I need to solve. And, essentially what we're kind of doing in our first order fluid solver is rewriting it to look like this, and I'm going to be saying that kind of the transported u, or say the new velocity minus the transported old velocity divided by delta t will be the negative scaled pressure gradient that makes the new velocity divergence free. And this is basically this is the classic way of writing the first BDF method, which is also called backwards Euler, which is a name that you might have heard of if you haven't heard of BDF1. So these actually are the same thing. And in our fluid terms, this is really what it translates to. But this is like a really crude estimate of the derivative. We can do better than that. So in particular, let's look at BDF2, which is the second order BDF method. And it essentially says, okay, I want to look at an estimate for dy dt at n plus 1, but I want it more accurate than that simple finite difference formula. So I can use an additional value of y going into the past. So I can use yn plus 1, yn, and yn minus 1. And if I remember correctly, the coefficients that I need are these ones. And you can derive those coefficients by making sure this is exact if I plug in a quadratic, but I'm not going to go through that math here. So this is well known, and it turns out to be a very accurate integrator. In fact, you can generalize this to using even more terms in the past, more history, and higher order finite differences and get a more accurate method. If you go too high, you start hitting stability problems. So it's probably for graphics, BDF2 is actually the sweet spot, at least for now. In the fluid case, though, nobody's really investigated this by incorporating transport the way we do in graphics. There have been BDF2 integrators used for fluid flow, like in engineering science flows, where they use very small time steps. But that's kind of too expensive for us. We need to get results much faster for the scale of shots that people want to do in graphics. So we need something a little bit different from what's been done before. So this is a new method that we have invented here for Aero, which we're calling material BDF or MBDF. And essentially it looks something like this, where we'd take 3/2 times the new velocity field minus 2 times the nth velocity field, but transported. So it's been through a transport to get it onto the time n+1 grid, but we haven't done any physics to it. And we'll also include the n-1 that's basically being transported twice to get from the n-1 grid to the n grid to the n+1 grid. All divided by delta t is again going to be -1 over rho grad p, and we're solving pressure to make the new n+1 velocity field divergence free. Turns out this is actually a little inconvenient to work with. We'd have to save values from previous time steps and look them up, and if the time step changes, if you have a different number of steps in each frame, this gets a little hairy. So we actually incorporate a different channel, which we call the material acceleration, to smooth out the math here. I'm not going to go into the details. But in the next section of the video, let's actually take a look in a Maya session of what this buys us in some simple scenarios, just to give you a sense of why this little bit of one extra channel to store and a tiny bit of extra math can actually make a big difference for some scenarios. To demonstrate the improved time integration, I've brought up Maya here with a very simple scene. So basically the only geometry here is this simple twisted gear shape, which I have selected. I just basically want some interesting geometry that's simple to create and is not too regular, so we'll get some nice details out of the smoke simulation. And then I've created a Bifrost graph and edited it. I'll just bring that up to show you. All I've done in this case was selected the mesh, brought up a basic Aero graph, exploded that so I can start playing around with it. In particular, I've set the input, which is that twisted gear, as the source, and I have set it to only be active on the first frame, set up the resolution of my simulation, the smallest cell size, grid cell size. I've set it to emit a puff of smoke with a particular fog density, and also a really strong kick upwards in the initial speed, which I'm setting in the fluid simulation. I don't have any colliders here, so I'm ignoring that. The Aero solver settings, I have set the style of the transport from the default smooth, which is like a first order method for transport, which is fast, but kind of gives us a lot of numerical dissipation. So I've set it to busy so that we don't have to worry about that source of error, and we can focus on the time integration. I've disabled buoyancy just for the sake of simplicity. And the other important thing here is I've set the max steps to 1, so we know for sure the solver is only going to take a single time step each frame. And this will really show the difference between the improved time integration and not. You'll notice there is no checkbox to actually turn on improved time integration or not, because it's so cheap and gives us such a good effect. That's not one of the easy to access defaults, but of course we can always set the property ourselves on this object. So I've basically created a Boolean to either enable improved time integration, which is the key here for our solver properties, or not. And I will look at simulations both where I have improved time integration false or true, and we'll be able to really see the difference. So let's take a look at some play blasts of this simulation now. So let's look at the simulations, first using the old time integration, the first order method. And although the transport gives us a lot of nice detail in the smoke, when we run it with the improved time integration, you'll see that we get a lot more energy conserved, a lot more angular momentum in all those circular vortex regions at the top and the bottom. They travel a lot further, they look a lot better. Given the small extra cost and the huge improvement in quality you sometimes get, it makes it obvious why we have this as the default.